So I wanted to give you an update of my view on how maybe molecular science, molecular simulation is developing and what deep learning can do for it. And I have to admit that with my change to the new role here at Microsoft that Xavier has mentioned, this view actually has changed a lot in the last couple of months. So I've kind of updated a lot of my beliefs, and I'll talk a little more about that at the end. Most of my talk will be on work that's from the university time, because obviously we just started and there's not too much to report there. And yeah, so just to mention that, so Microsoft Research has started this new initiative, AI for Science, which is basically developing machine learning tools and systems for scientific problems. And actually most of what we're working on is molecular science. There's also PDE, partial differential equation group, but otherwise mostly molecular systems and molecular challenges. And Max is here, so he's from the Amsterdam team. We're in Berlin, and then there's also Cambridge, Beijing, and then somewhat smaller groups in Redmond and Shanghai. And this is a view from our new Berlin office here to Alexanderplatz. So basically that's that part of my life. But as I said, most of the talk will be kind of from FU Berlin time. So this is my FU Berlin group. And so let's get into it. So we're developing basically machine learning systems to enhance molecular simulation methods. And why do we do that? Because basically we want to develop methods that kind of empower people to do things like this. There are lots of interesting, important challenges that are relevant for society that can be affected and impacted if we understand better and get more control about molecules. So drug discovery, of course, is a famous example for that. It's also an example for a process that is extremely tiringly slow and complicated. And I think we still have yet to see that AI methods and simulation methods and the combination thereof actually make the process faster and more effective. But we're looking to people like Patrick to actually make that happen. So, and of course, similar challenges exist in material science, where we're basically trying to find materials with new properties, and we have this enormous combinatorial search space that we hope machine learning and simulation and their combination can help us with. Same in catalysis, right? For example, the production of ammonia, that's one of the processes that produces several % of the world's energy output. So if we can improve some of these processes, we can actually have a very big impact on energy production, for example, and energy efficiency. And another important one is green chemistry, right? So a lot of the kind of rules of organic chemistry, so how people make molecules from stuff, is kind of based on very old rules that often go back to petroleum products. And there's probably this huge space of synthetic synthesis rules that are using renewable products, but that's kind of a new corner, and a very little known corner of chemical space. And hopefully these tools can help us to explore this space. How do we do things? So basically, there are sort of two ways you can use AI and computers to help with chemistry. So one is obviously to somehow combine that with robots and automated labs to actually automatically explore making things, finding new reactions, for example, or optimizing properties of molecules. And the other one is, so to say, the dream of quantum chemistry or theoretical chemistry. So let's just replace the lab with a computer, so basically a virtual lab, and try to predict as many things as accurately as possible with the computer. Of course, in practice, we kind of need both, but so this is what we are focusing on. So basically enhancing molecular simulation with machine learning. Now, this workshop is about emergence, and Molecular science is very much a science of emergent properties because most molecular problems are really multiscalar. So we have the quantum scale here, so electronic structure scale. In principle, we have scales below that, but in chemistry, we're usually starting at the electrons. And then, of course, we have like molecules and molecular systems, maybe simulation boxes, pieces of materials, biomolecules, cells, etc., and eventually macroscopic systems. And in each of these higher scales, there are properties that are emerging from the rules of the lower scales. And this is kind of almost like a bread and butter problem for us in molecular simulation, because we usually parametrizing or learning systems at some scale that we think is a good scale to model our problem in. That could be like a molecular dynamics force field, it could be a quantum mechanical Hamiltonian, and then we somehow simulate it. We insert it into a simulation procedure, and from there we compute some macroscopic properties, some observables. And we do that because we believe there are somehow physical models that are that can be well parametrized with these parametric models and that do a good job in predicting the next level. But of course, when you do that, there will be errors that are somehow cascading as you go to the next scale, and we want to control these errors, and we have to think about how to do that. One of the issues with these multi-scale systems is that, unfortunately, we are not equally good at all scales with our theoretical description. In fact, we are pretty good at the lowest scale. So for small molecules, where we can afford very high-level quantum theory. And we're pretty good at the very large scale, where maybe we have continuum models and where a lot of problems are going away. Like we don't have the stochasticity of single molecules. We don't have quantum effects anymore. So these things are kind of averaged out at the macro scale, and we have full observability. That's a huge reason why doing anything on the molecular scale is so difficult, because we can't really observe molecules directly, because there's this diffraction limit of optical light, which basically just limits us to see things that are 250 nanometers or bigger. And whenever we want to see something that's actually smaller, resolve something that's smaller, we have to do tricks, and we have to do indirect observation, and we have to we need models to reason and to explain these observations, what might be happening at this scale. Right? So there's this in-between region, or scales, where we're not very good with our models, because we're kind of building models on theories. But obviously, every year we're getting a little bit better and push this boundary. And machine learning methods have really helped to push this boundary a lot in the last couple of years. And we are seeing this in some molecular simulation systems already. And I think we'll see a lot more in the next couple of years, where as we are transitioning from kind of a field that is applying machine learning methods and show that it's possible to do things that we did without machine learning before, to actually using machine learning to make things really more efficient or more accurate, or both. Okay, so I'll focus on basically two things. One is on quantum chemistry and electronic structure, and the other one is on sampling. On quantum chemistry, basically our starting point is the Schrodinger equation. Let's start at the time-stationary Schrodinger equation. So basically the main goal is to solve this eigenvalue problem for a given Hamiltonian, which is just describing the protons and electrons in our system and their charge interactions. And so basically we're just looking for the eigenvalues and eigenfunctions of this equation. And to make it even more simpler, let's look at the ground state for now. So the first eigenvalue-eigenvector pair. And that seems like a pretty simple problem, right? So solving eigenvalues for matrices, that's not rocket science. But unfortunately, there are a few nasty things about this particular eigenvalue problem that make it very hard. And so, as stated by Paul Dirac 90 years ago, more than 90 years ago, this is still absolutely valid. So we know the equations. This equation is really a great description of our problem, but unfortunately, we cannot solve it very well. And basically, most of what we're doing is to try to find numerical approximations. And unfortunately, solving this equation, as several other equations for molecular systems, is, if we want to be really accurate, is kind of exponentially hard in the system size. So in this case, the number of electrons, for example. And this means, of course, although our computers are getting exponentially faster over time, I mean, assuming this trend continues to hold, it's just getting a little bit easier every year. So it's not, this exponential growth does not really make a big change in our ability to scale up this equation, because it's also getting exponentially harder as we make the system bigger. So we really need good approximations, need to continue to develop good approximations and maybe machine learning methods to help push the boundary. And so quantum chemistry is a good example of an area where we have, first of all, we have many methods, because the field is very old. It's like 100 years old. So people have developed numerical approximation methods all this time. So this is a very, very mature field. And there are, there's actually a good reason why we have all these different methods, because there's a trade-off, several trade-offs, but an important one is between accuracy and efficiency. And one way to phrase efficiency is, what is the effective system size, so the size of the molecule that you can actually treat with a given method. And then we have this trade-off between system size and accuracy. And there are sort of different generations of methods. So here, sort of the older methods that strike a certain balance. And then there's a newer generation of methods that are somehow just better in terms of this trade-off. So for example, DFT, density functional theory, is a famous one. It's the most widely used quantum chemistry method, because it has a great trade-off between accuracy and efficiency, especially in the right hands, so in the hands of people that understand which function to choose for a given problem. And then there are different trade-offs here. So semi-empiric methods, such as density functional theory, time binding, is faster, more efficient, but also less accurate. And then force fields are generally understood to be, so they're certainly faster, and they're generally understood to be even less accurate, although that depends a lot on the exact application domain. You can have very accurate force fields for very specific domains when trained well. And then on the on the higher accuracy end, we have things like coupled cluster, which is generally considered to be a gold standard method. And we also have quantum Monte Carlo. And the very high end, we have full CI, which is basically the sort of the exponentially hard solution approach. Now, I would argue that machine learning methods can reach kind of a new frontier in this system size accuracy trade-off. Right? So first of all, it's good that we have different methods at different trade-offs, because we need them for different purposes. Yeah, we need somehow fast and less accurate methods, because sometimes we just want to explore and we want to screen things maybe in a computer and have a filter that kind of removes certain molecules or materials that we're not interested in and that don't have nice properties. But then we want higher quality methods, higher accuracy method to filter further and to validate. Alex?
Just to start with questions.
Yeah, sure.
So I think it's a nice diagram, right? But I think something that is not widely discussed is that there is a third axis, which is numerical complexity of the solution in these different methods, right? And which I think becomes much, much more important and has been, appreciated only in the past 10 years or so, that people can actually get closer and closer to the solution of, say, coupled cluster or quantum Monte Carlo,
Yeah.
and actually realize that they do not give the same results, right? So there are many classes of systems where QMC and couple cluster, right, do not give the same results.
No, absolutely.
And give very different results because of the complexity of describing the wave function, right? So in a way, when you go
So by complexity, you mean the order complexity, like the
complexity
scaling?
of just describing it, right? So how do you, because you always introduce a basis set, right?
Yeah.
And the basis sets in couple cluster, quantum chemistry code, and QMC have a completely different basis sets, right? And they don't guarantee that you actually converge variationally to the right.
Absolutely.
State, right?
Yeah, so there are different axes you can definitely draw, and where these 2 points would not coincide, for example.
That's right.
Also in terms of computational scaling, so in just how they scale with n, they are very different. Like Monte Carlo is the n to the 4 method, CCSD is n to the 5 to n to the 7, depending on which flavor you're using.
Can I ask a counter question? Why is that not the accuracy axis? I mean, if you have two things which give very different results, one of them is bound to be wrong, right? Or both of them are wrong.
But then these two dots would diverge, right? In accuracy, depending on the numerical settings that you use for expanding, the Hilbert space of your wave function, right?
But you're for a new axis. So what should be on that other axis rather than accuracy?
Numerical complexity. So in the force field, right, you only have coordinates of your atoms. That's all you need, right? So it's pretty easy. Yeah. In density functional theory, you need the three-dimensional electron density. So it's not an easy object, but we can handle it. But then in QMC and couple cluster, you need the many-body wave function, right? So it's much harder to
3n dimensional.
Are you arguing about a robustness point, right? Because it's relatively easy with force fields to get similar answers among fairly similar settings. Whereas if you change the settings on a DFT calculation, you can get more variant, and I think probably even more so with QMC, especially with some of the sampling. Is it kind of a robustness?
Right. One is reproducibility, which is something that people have started to do in the quantum chemistry community actually quite a while ago. But if all codes use the same basis, they will be reproducible. But it doesn't mean that they actually converge to the ground state, right?
Yeah.
Because, for example, you should take then a plane wave basis and demonstrate that with a plane wave basis you actually get the same result. But no one does it because plane waves are for condensed matter, right? While Gaussian expansion is for molecules. So it's pretty hard to meet in between. So that's good.
Yeah, good point. So my argument is with machine learning methods, what they could do and what they should do is basically to reach better trade-offs, to somehow reach better accuracies or better efficiencies compared to existing methods. And that, again, for different accuracies, we have different types of methods here. So the most obvious one, and also the most mature one, I would say, is basically machine learned force fields. And we'll have several talks in this direction, so I'm not going to dwell on that actually. So there's I think Tess is going to talk about that, and Alex for sure, and probably several others as well. But the basic idea here is usually because we have these quantum chemistry methods, we can do reference calculations, such as with DFT or the cluster, for various molecules, compute energies and forces, and basically store them in a database, and then train in a supervised manner to predict these energy functions as a function of the coordinates and of the composition of the molecules or the elements, basically. Right, and this is a very established approach to do this. It's also very nice from a machine learning point of view because it's simple, basically just a supervised learning problem. Of course, now there's an understanding that probably you have to go to active learning in order to kind of iteratively explore the parts of the space that you don't have much data on, etc. But so this is super established, and basically you'll be a little bit slower than with the classical force field because the functions that we are evaluating are more complicated. So maybe it's a factor 5 to 10 slower. In some cases, it's a factor 100 to 1,000 slower, depending on the architecture. But there's certainly a potential to be within a similar order of magnitude in terms of speed than force fields, and we can be a lot more accurate, and we can incorporate quantum effects that normally wouldn't be in a force field, which has like a fixed bonding topology. Yeah. But we can do other things as well. So for example, we can kind of sit on this DFT point here and then build machine learning in there and try to machine learn functionals in order to basically get better DFTs, because DFT is in principle an exact method. Yeah, it's basically a sort of a mean field formulation of the many-body electronic structure problem. But it's understood that there exists in principle a universal functional of the density, that if we knew that, and if we let the electrons interact with that and solve the self-consistent equations, we would have an exact solution. Unfortunately, we don't know what that universal functional is, and we have no systematic, like, variational way of finding it kind of self-consistently within the method. So that's something we have to insert into the DFT method. And then once we have defined this functional, then we have a variational principle that will solve the electronic structure problem within this functional. Okay. And so there are several approaches in this direction, and one of them that's worth mentioning, of course, is this DeepMind work from last year, 2 years ago actually by now, where they have basically trained a neural network based functional on high quality quantum chemical data, and then use the Kohn-Sham approach, so a self-consistent iteration in the Kohn-Sham formulation to basically solve the electronic structure problem in this functional. And I think this is just like a first step on the way. This new functional is probably not a revolution from a practical standpoint for DFT practitioners, at least that's my understanding. But it shows that we can make progress with machine learning methods in this direction. And so what I want to spend a few more minutes on is this next higher level, which is quantum Monte Carlo. And quantum Monte Carlo now is basically the next more complex approach to approach the electronic structure problem, where we're actually directly trying to solve the many-body Schrodinger equation. And quantum Monte Carlo is a very nice method. First of all, it's very simple. So I always like methods that are simple because I can understand them. But also it's conceptually very nice because it's a variational method. So basically, instead of looking at the eigenvalue problem, we look at this variational formulation where we're minimizing the expectation value of the energy, which is a functional of the wave function, so of this 3 n-dimensional function. And so we just have to search for the wave function which minimizes this functional. Right? And this is in the limit that we find the minimum, this is exact. So the only limitation here really is how much freedom do we have in expressing this function? So how general is our ansatz? Can our ansatz actually fit the true wave function? But of course, it's a 3 n-dimensional problem now instead of a 3-dimensional problem as in DFT. So it's also much harder and computationally more costly. Okay, and yeah, basically the idea here is to use a neural network for this ansatz. This has first been proposed by Giuseppe Caleo and Matthias Stroyer in this paper here, where they basically use this idea for spin systems. So basically for spin lattices, and these were bosonic lattices. We are interested in molecules that have electrons. Electrons are fermions, and they are unfortunately a little bit more nasty because they give rise to antisymmetric wave functions. But I'll come to that in a minute. The basic idea here is to treat electrons really as particles, as pseudoparticles, and have them run around the electrons. And we are sampling this sort of electron diffusion with a Monte Carlo approach. The probability density from which they are sampling is the square of the wave function, which is, of course, the quantity that we're optimizing over. So it's going to change over time. So that means we have to run Monte Carlo in every iteration of the optimization. And the Monte Carlo idea is basically to replace this functional here by this expectation value over the electron density, the 3n dimensional electron density. And the quantity that we're averaging over is the so-called local energy. And if you look at it, this is basically just solving the eigenvalue problem for E. And that shows you that once we have the exact eigenfunction, so in that limit that our method has found the exact psi, this here on the left is actually an eigenvalue and thereby is constant in the electron positions. And that's the nice thing about quantum Monte Carlo compared to other Monte Carlo methods. I mean, normally Monte Carlo methods converge with 1 over square root of n, where n are the number of samples, right? That's how the variance of an expectation value that you're computing shrinks with n. So that's pretty slow. But in the denominator of this expression is the variance of the quantity that you're averaging over. And that becomes 0 in the limit that psi converges to the true psi. And this is why quantum Monte Carlo is actually a useful method, because we are trying to find really tiny energy differences here. So if our method would just be converging with 1 over square root of n, it wouldn't be very useful. But in this limit is actually quite useful. Okay. So electrons are fermions. This is why we have this extra constraint here, which is the exchange antisymmetry of electrons. So our functions have to fulfill this eigenvalue equation, but they also have to satisfy this constraint that when we exchange 2 electrons with the same spin, the sign changes, which induces these nodes in the structure of psi and also in the structure of the probability density, psi square. And that makes the whole problem super horrible to solve, basically. And this exchange argument is essentially what makes the problem exponentially hard. Okay, how do we approach this? So in standard quantum chemistry, people are using determinants, Slater determinants, in order to express antisymmetric functions. And the basic idea is you take your n electrons, you select n functions, and you basically evaluate these pairwise. So every electron, every function, write it into a matrix. And because it's organized such that an exchange of 2 columns, 2 rows corresponds to an exchange of electrons, the determinant of this matrix will be an antisymmetric function in electron exchange, which is exactly what we want. But this is just one building block of your antisymmetric function, because you have many ways of choosing n functions to build this matrix. And so even for a fixed basis set of functions, you have exponentially many ways to do that, which is basically why this method scales exponentially if you want to be really, really accurate. So the idea now is to kind of move the hard part away from this discrete combinatorial part where we really cannot do much about the exponential scaling to basically finding better functions. And that's the so-called backflow idea. Again, that's not a new idea. This has been proposed before, and in particular in the quantum Monte Carlo world. But I would say before neural networks, it hasn't been used in a very successful way, because you need really quite expressive function in order to make that idea usable. And so what backflow does basically is it's a function which takes the electron positions and then transforms them, but does that in a many-body way. So basically any position at the output here will depend on all the positions at the input, but it will still have the same exchange property. So when you exchange 2 electrons at the input, the corresponding particles at the output will also exchange. So with that, you can now enter your Slater determinant again, compute an antisymmetric function, and that's something that's presumably much more expressive than a single Slater determinant with fixed functions. And that's the basic idea. So here we're inserting our neural network function to learn this transformation and then train everything end to end. And the whole system then, this is Paulinet, looks like this. So basically this is a graph neural network that receives the nuclear and the electron coordinates as inputs, transforms them, and generates the component of the Slater matrices. And then there are a couple of other tricks here. And over time, we have figured out that some of these tricks are really important, and some are actually rather counterproductive. So one that's necessary is the computation of the Slater determinants so that we can actually have an antisymmetric function. If you would remove that, then you would just not find the right solutions. Something that's really helpful is this so-called Jastrow factor, which is a symmetric exchange, symmetric modification of the function, which is not strictly necessary in order to express the true wave function, but it turns out to be really helpful. This is also in normal quantum Monte Carlo methods that do not employ neural networks. That's actually the only thing that you're training usually. And there are also variants where you're training additional coefficients, but kind of like bare bone quantum Monte Carlo is you start with a wave function expressed by a Slater determinant or a couple of Slater determinants. You multiply this Jastrow factor to it, and you just optimize its coefficients. Yeah. Electronic cusps are really useful as well. So that's basically asymptotics. So as two electrons approach each other or an electron approaches the nucleus, we know the wave function has a certain asymptotic behavior, and we can fix this. And this is very useful because in these limits, the probability density to find electrons there is very small. So we would sample these states rather rarely, and if then we had functional values that were quite off, then we get basically a big error, and that's bad for our learning. So this helps learning a lot, building this in. And this thing here, Hartree-Fock, so starting basically with the standard quantum chemistry method to start off the orbitals and just learn the change with respect to the standard method, we thought was a really brilliant idea, but it turned out that this is actually counterproductive. So it turns out it's really much better for the whole learning dynamics and for the ability to converge to good solutions to start out with something rather silly here and just kind of some sort of radially symmetric orbitals and let the neural network figure out the rest. So that's...
Does it mean that Hartree-Fock is a really bad approximation?
I mean, in many cases, it's really helpful. It's almost always helpful to quickly converge to a decent solution. That will converge faster than if we don't use Hartree-Fock here, or cusps-SCF in general for multiple determinants. But it can be misleading, because Hartree-Fock and cusps-SCF, you make choices. Basically, that's what I meant before, right? At this point here. For every determinant, we're making choices, which of these functions we're using. And there's a certain, for a given basis set, there are certain algorithms how to choose the first n determinants, right? And if this algorithm doesn't pick the ones that are actually good approximations to the solution of the problem, then you're basically sending your machine learning algorithm or your neural network in the wrong direction, and it can just get stuck there. So it becomes a learning problem. In principle, the network should be able to recover from it, but sometimes it doesn't. So it's... You had a question, Max?
Yeah, something about the Jastrow factor. So can that factor not actually also be learned in the backflow? Is it giving you extra flexibility that is not already represented somewhere else, or is it imposing some inductive bias like the cusps, which are super useful to learn faster with less data?
It can be learned here. So it's we don't, in principle, need the functional flexibility, right? It doesn't add functional flexibility. In principle, even one single antisymmetric determinant would be enough to represent the true solution. But in practice, we see that multiple determinants and using the Jastrow help us to find good solutions.
It's an over-parameterization.
Yeah. Mm-hmm.
I have a comment about this. Actually, there is a physical reason behind the Jastrow. Mm-hmm. So in Hamiltonian, you have one body terms and two body terms. right? And two-body excitations are actually bosonic, they're not fermionic. And so because of that reason, just-rho factor really helps because it's a symmetric function and not antisymmetric. So electron correlation is dominated by two-body excitation. So you exchange pairs of electrons. And so your wave function is symmetric in that case, right? So there's an additional symmetric wave function on top of the antisymmetric one. Because we don't actually know how the wave function should behave to exchange of 3 electrons, for example, right? It should also be antisymmetric, right? But they are all mixed excitations in the wave function. And so just-rho factor, it basically models this two pair correlations, right?
Yeah. Okay, so I see my time management is rather not that great. But so, and these are still kind of old results. So basically what we showed here, that with this approach you can get very high accuracies for these small systems with a lot less Slater determinants than with traditional quantum Monte Carlo method. So basically the idea here is you just give the method like a budget of Slater determinants to work with, rather few, like 10 or so. And then you basically put all the power in the neural network that learns how to generate the matrix entries. And there are some systems that look rather harmless, but are very difficult to solve with classical or with standard established quantum chemistry methods like this one, cyclobutadiene, which does this transition between this rectangular and this square transition state, which is basically a highly correlated state. And you actually need something like an n to the 7 method in order to get a good approximation of this energy barrier. But with Paulinet, which is the n to the 4 method, if we fix the number of determinants, of course, we get there as well. And it's really, in that sense, it's a black box method because the only thing that is different between this system and that system in terms of training the network is we give it a different Hamiltonian and just learns that solution. Whereas these methods here, like this multi-reference coupled cluster methods, usually they involve quite a bit of expert knowledge in designing them or in making certain choices for a certain molecule. And so what we've done in more recently is to also extend it to excited states. And the idea is basically the same. So now we want to solve for multiple eigenvalue, eigenvector pairs of the Schrodinger equation. And we basically have an ansatz that could be basically the same network with multiple outputs. In this case, we just use multiple networks. And we have constraints between these networks so that they're actually finding orthogonal eigenstates. And the basic idea here is to add this penalty term, and this penalty term has to be designed such that once you are in the solution, so you found two eigenstates that are orthogonal to each other, and now you make them non-orthogonal, you start making them overlap. You want that this penalty grows faster than your energy reduces, so that basically it always wins, and that in this optimal limit, in the zero variance limit of quantum Monte Carlo, you actually find the orthogonal solution. And that's the case for, I mean, that depends on the choice of the function, but for this function, for example, that's the case. So we can take systems like this. This is lithium hydride, so small system again, and really find like 6 eigenstates, and these are the energy differences of these 6 eigenstates to the ground state. So that's why you see 5 lines. So that's rather neat, and here we've applied the same idea to benzene, basically, where we get quite accurate results as well. Now this is already a calculation that takes a couple of days with this quantum Monte Carlo method. But compared to other very high-end methods, this is relatively fast. So I mean, it's going to be a lot slower than DFT or a coupled cluster. But getting accurate excited states is actually quite hard. So for many methods, you can be quite far off there. And what you can also do is to compute conical intersections. So basically, Conical intersection is something where you have, so in let's say the ground state and the excited state, you will have an energy, right? And energy as a function of the nuclear coordinates. And then there might be certain positions, certain nuclear coordinates, where these energy surfaces meet and where you can basically transition between the two states. And so where this is, for example, relevant is in fluorescence of molecules, where you perhaps excite the molecule to an excited state with a photon. So bring the electrons to a kind of a higher energy state. And then the molecule will do its dynamics in this excited state energy surface, where it's maybe easier to undergo certain transitions that are hard in the ground state. And then at the conical intersection, where the two energy levels meet, it can fall back to the ground state. And this, for example, is what happens in rhodopsin, which is a pigment in your eyes, which has a little molecule, which is very hard to isomerize. But it can be isomerized if it absorbs photons at a certain wavelength. And then it does this transition, falls back to the ground state, will just dissipate heat then basically, and as a result of this conformational change, there will be a signaling cascade, which in the end leads you to seeing something.
I didn't quite catch what the plot in the bottom left, like what quantity that was predicting in the bottom.
These are two different angles of this molecule.
More left.
Sorry?
More left.
This?
Yes. Yeah,
these are just the energy differences between the ground and the excited state. So the excitation energy is computed with different methods.
Got it. Thanks.
All right. What's the time situation? We have at the hour, right?
I think it should be 9:50, but you get extra time because of the questions. So yeah.
Okay. So I'll do a short run on sampling, which is a completely different problem, right? So but also a very interesting problem. So sampling the equilibrium distribution of molecular systems, that's something that's extremely important and has kept us busy for many, many years, and still keeping us busy. And this is an illustration for a protein, which undergoes some dynamics in the milliseconds timescale. This is from a simulation, so take it with a grain of salt, but I believe it's qualitatively quite realistic. So there's a lot of dynamics in these systems. And these are different states that the molecule transitions between. And what we're really interested in computing are usually macroscopic quantities such as, for example, an equilibrium expectation value. So that it could be something like the probability that a molecule will bind another molecule, like a drug will bind to a protein, or the probability of a protein to be folded. And likewise, there could be dynamical expectation values such as transition rates, for example. But the difficulty here is that these are always like integrals over the equilibrium density times something. And it's unfortunately very difficult to sample this equilibrium density because there can be high energy barriers in the system, so there can be long waiting times to transition across these barriers, so the mixing of these Monte Carlo chains or whatever we use to sample them is quite slow. And this has been a problem that's basically been around for 70 years. So we're talking about quite old problems here in general. This is sort of the first molecular simulation paper, if you like, from Metropolis. Equation of state calculations by fast computing machines. And this is still a huge problem. So if we want, for example, to simulate this process where these two little proteins bind to one another, that could cost us a GPU year to observe a single binding event and 1 million GPU years to see a single dissociation event. So this is really, without applying any tricks, this is quite an impossible problem. So all of these 70 years, people have just looked for various tricks to speed up the problem. These are basically called enhanced sampling methods. And again, there's like in electronic structure, there's a gigantic zoo, an ocean of methods that are addressing different aspects of this problem. And one of the approaches that we've worked on a lot is Markov state models, which is basically sort of a divide and conquer approach. You kind of explore the system. Markov state models have basically a lot of intelligence in how to understand where different long-lived states are in this high-dimensional conformation space. And then you use this in order to kind of generate a map of your conformation space. And you can update that while you're generating new simulations, and you can use it in order to inform where to start new simulations from. But in the interest of time, I will skip over this part. And just going back to these two proteins. So with this kind of approach, one thing we can do is we can basically leverage many short simulations and kind of combine them in this map, in a Markov chain between the long-lived states in order to get a complete picture of our binding and unbinding process. And we can do that with a total time of 2 milliseconds worth of simulations in thousands of individual simulations that are each something like a microsecond long. And that's much, much shorter than the time you would need to wait in a single long simulation, like 5 orders of magnitude shorter. But it's still a lot. And in this particular example, this is a movie of the binding trajectory. In this particular example, it takes us about 20,000 GPU days, or the equivalent of 500 gigajoule, in order to compute this solution, which is a substantial fraction of what it takes to shoot a payload of 50 ton to the moon. So thinking about it in this way seems a little bit inefficient, the whole process. So this is why we're looking to machine learning. And because in machine learning, there are these wonderful generative models that are doing really impressive things. For example, so often these methods are trained on data. This is a data set of images of celebrities. For some reason, that's an important benchmark in machine learning, to be able to generate celebrity pictures. And this is actually the output of StyleGAN 2, so that's not a very new method for machine learning standards. This is already retired, basically, 3 years ago, StyleGAN 2. But I mean, the pictures are still extremely impressive, I think, and these people all look real, right? So but they're completely made up. So how do we leverage that for molecular simulation? So there is a family of different generative learning methods, and one particular interesting one for molecular physics is normalizing flows. So normalizing flows are invertible neural networks, which are usually used in this way, that you start from samples from a simple distribution, something like a multivariate Gaussian distribution, and you let the network transform them into samples of your target distribution. And because the network is invertible, you can leverage the transformation of random variables rule for invertible transformations, which allows you to express the probability density of sampling in output X from the network, given that you know the probability density at the input, and you can and assuming that you can compute the Jacobian, so the first derivatives throughout the network. And for certain neural network architectures, you can do that. And again, there's a whole zoo of flow architectures, basically, of methods to construct such functions and trying to make them more expressive or easier to train or more efficiently computing these Jacobians, etc. And there are some methods like autoregressive methods which are just formally invertible but not efficiently invertible. So it always depends what exactly you need of your method. But so this feature makes these methods super interesting for statistical physics, because we can then basically train them to match a target distribution, a target density. And in many cases in physics, we have that. We will often start with a situation where we know the Hamiltonian or the energy function. We know the statistical ensemble in which we want to sample. So we can just write down the probability density we want to sample from. It's just difficult to do. It's just difficult to get mixing in this, in a Monte Carlo chain or a simulation in this density, right? So in 2019, and that was just before our IPAM long program that we had in 2019 on machine learning for physics, we developed this Boltzmann generator, which is basically was a first attempt to do that for molecules, and is basically training a normalizing flow to learn this density that approximately generates a Boltzmann distribution, and then uses some sort of reweighting method, such as just a Monte Carlo acceptance step, for example, to unbias the density. And with this, you can train Boltzmann generators that sample, for example, transitions like this. So this is a dimer opening closing transition. There's a barrier when you are opening the dimer. But the transition is quite complex because the system is densely populated with these solvent particles. So you have to push the solvent particles around when you want to open or close the dimer. It's not just a simple Monte Carlo move. So the method has to really learn like a many-body transformation in order to be able to sample these transitions. And you can also, with a lot of tricks and the right representation and parameterization, sample small proteins with this kind of approach. Now, one thing, I will skip over this part, unfortunately. One generalization of this idea is you can actually go away from this exact invertibility of the functions. So it turns out if you, instead of expecting that you can really invert these functions point by point, one thing you can add is you can add stochasticity in between. So for example, you can have like invertible layers, and then maybe occasionally you just do a step of Langevin dynamics or some Metropolis Monte Carlo or whatever you want to do. And so this is what we then call a stochastic normalizing flow. And interestingly, you can still train this object to match target densities. And what happens here is that you have to replace your Jacobians in the functional that you are training with these quantities, and these quantities are basically just log ratios of forward and backward probabilities. So whenever you have some stochastic operation here, it has to be statistically reversible so that you're able to compute such a ratio. In other words, whenever you have a finite probability to make a forward step, you have to have a finite probability to make the backward step as well. But it doesn't have to be point-by-point invertible. And otherwise, it just trains like a like a usual normalizing flow. So that's a very, like, algorithmically, that's a super trivial change. You just kind of have to be able to compute this for whatever stochastic operation you're doing here, for your Langevin dynamics or whatever you're doing. And then you just insert that at the same place where the Jacobian would be otherwise. And this helps you a lot because it can break some of the constraints that the neural network has when it comes with this invertibility, with the necessity to be exactly invertible. And you see that especially in low-dimensional functions where this is the exact function, it's just a 2D function. We just used images, basically the density of images, to define this function. So these are low-dimensional but very complicated functions. And you can see that a real NVP transformation, which is a simple normalizing flow architecture, does a quite bad job in approximating this image density. This is what a pure Metropolis Monte Carlo sampler would do if you start the sampling from the point in the center, and then you just make Metropolis steps and you accept or reject according to this density. Of course, eventually this will converge if you make the chain long enough. But for a short chain, this is sort of what you get. You still kind of have your initial distribution in there. And if you just take these two things together, so this flow transformation, which does a horrible job, and this Monte Carlo sampler, which doesn't converge, and just put it in one network and train a stochastic normalizing flow with it, this is what you get. So you get a huge boost in expressiveness without really paying anything extra. But stochastic normalizing flows, for several reasons, they haven't been really used too much. And but the new kid on the block then basically are diffusion models. And that's what everybody's using now, basically, us included. And the reason why these are so popular, and these have been around for the idea has been around for some time, but basically these denoising diffusion models now incorporate a few ideas that make these networks much more expressive and easier to train. So first of all, we have to give up something. We have to give up the ability to easily compute the exact output density of the network. So actually matching an exact target density is going to be harder with this approach. But the advantage is that we have this so-called noising operation, which actually starts from our data point and then successively adds noise. And the way this is defined is it allows you to immediately jump to any of these time slices here, of these virtual time slices, and generate the noisified image. So to say, we can, and then basically what the network has to learn is just this denoising operation. This is if you unfold this in these two pathways, this is basically like a variational autoencoder with a fixed encoder, where the encoder is just this noise operation. And we only learn the decoder. And because we can sample pairs of time slices, we can do that very nicely during our neural network training, where we just sample random pairs of time slices and we just update this denoising operation. And then additionally, usually what's done is this denoising operation comes from sort of a Langevin dynamic step, where we're just learning the so-called score function, which is basically the force. And we're using usually one neural network, which is just parameterized by time, but is shared across these time slices. And a combination of these things makes these networks super nicely trainable. And also, we are very free in what network we choose as the force function here. So that's a huge advantage compared to normalizing flows. We can just be very, very flexible and choose whatever architecture is interesting or relevant for our problem. And that's basically just a plug for Max talk, I suppose. If you're going to talk about that, that's one of Max's paper, which is very nice, something that we're also building on now, denoising diffusion models for molecules, which incorporate some of the symmetries that are found at molecules. Yeah, and with this, basically I'm done. I didn't really talk about everything I wanted, but that's life. And it was a very nice discussion anyway, and thanks for your attention.